Hi. Every day we use things manufactured specially to cater our specific needs. Be it something as simple and small as a toothbrush or complicated and big as airplane. Engineers and researchers all over the world spend considerable time in tuning its mechanical properties so that it can serve its purpose at the finest and the cheapest. Many of these materials are soft materials and they are called viscoelastic, portmanteau of the words viscous and elastic. A viscous material like honey or water starts flowing with some resistance when a force acts on it. When the same force acts on an elastic material like the spoon, it deforms and comes back to its original form and shows some stiffness. A viscoelastic material shows both these behavior, but the material properties change with time and some other parameters like temperature. In the next 30 minutes of this video, we will discuss why it is important to understand and characterize the change in these material properties with time. An excellent material to explain the viscoelastic behavior would be silly putty. The putty, if we throw it hard enough, bounces off the floor like a solid. But if we keep idle for a long time, it flows. The material response is a function of the time delay between the cause and the effect. The response is a decreasing function of time, much like the fading memory. This can be quantified by the superposition principle given by Ludwig Boltzmann. Any material can be described by the stress-strain behavior. Stress is the force per unit area, and strain is the percentage of elongation or deformation. British physicist Robert Hooke in 1660 did some experiments with metallic springs and discovered that the deformation is proportional to the force exerted on it, or stress is proportional to strain. Today we know this law as the Hooke's law. The solids or materials which obey this law are called Hookean or perfectly elastic solid. Metals are Hookean in nature. Sir Isaac Newton, only a few years later, did some experiments on liquids and found out that the forces acting on a liquid is proportional to the rate of change of deformation. These materials are now called Newtonian liquids or Newtonian fluids, and this law is called Newton's law. Water, honey are some of the Newtonian liquids today. In the late 19th century, people started experimenting on newer materials like silk, rubber. When under load, some of these materials behave like solid, and initially they resisted deformation. However, at longer times, they would start flowing. Today we know that they were all dealing with viscoelastic materials, but at that time they didn't know about it. The uniqueness in a viscoelastic material is its combination of both solid and liquid-like properties and its dependence on time. To diagnose why it behaves like this, we have to shrink to the molecular level.
You would enter a reality. Become irrelevant. Become irrelevant. Time and space become irrelevant.
The combined first and second laws of thermodynamics state how an increment of mechanical work done on the system can produce an increase in internal energy or a decrease in entropy. This excess energy supplied by the load is stored in the deformation of its bonds. This excess energy can only be conserved or can be dissipated in a number of ways, such as heat, sound, surface energy, plastic deformation, or kinetic energy. In a Hookean solid, atoms are bonded together by strong metallic bonds and are stacked perfectly in 3 dimensions as lattices to form crystals. Hence they have a definite shape. Of course, in real life there are imperfections and anisotropy in the lattice. Upon deformation, the interatomic bonds stretch and store the energy as internal energy. This is the response of a perfectly elastic solid. This kind of elasticity, or Hookean elasticity, shouldn't be confused with the elasticity of rubber. A rubber consists of long chains of molecules, cross-linked to each other to form a network. In the non-deformed state, or the equilibrium state, the chains writhe and are in random conformations. Upon deformation, the excess energy is dissipated as heat. But now the chain is stretched and has fewer available conformations. The molecular chain withdraws and relaxes back to its equilibrium, or the highly disordered random coiled state, by a restoring force. This is rubber or entropic elasticity. In a Newtonian liquid, intermolecular interactions are very weak. As a result, the molecules are disordered and the material is said to be amorphous. Hence, it takes the shape of the container. When a force is applied to such a material, the molecules relax immediately and the excess energy is dissipated as heat or kinetic energy of the molecules, causing it to flow. Molecular structure of a viscoelastic material is quite complex and is composed of very long chains of covalently bonded atoms, much like the rubber. When subjected to an applied stress, these materials may deform by fundamentally different atomistic mechanisms. Intermolecular forces are low and the material is amorphous in nature. When cooled below a certain temperature called the glass transition temperature, the mobility of the molecules becomes negligible and it forms a glass which is vitrified or frozen form of the amorphous state. The space available to the molecules to move its segments is often visualized with having a free volume. Hence, for a glassy solid, the available free volume is minimum. When the deformation is applied, the molecules can't move much and the excess energy is stored within the chain backbones and the material behaves like a Hookean solid with a very high stiffness. The molecules in this regime can only relax to the equilibrium state by making very small configurational rearrangements like bond distortions. As the deformation time is increased, with mutual cooperation, the molecules translate and depart further gradually but slowly. The system has more free volume to relax to its equilibrium state and is said to be in leathery state. Long-range configurational rearrangements are still suppressed and a retarded elastic response is obtained for any deformation. The ease in relaxation of molecules can be observed by a dramatic reduction in modulus. Upon further increasing the time of deformation, the system resembles more like a cross-linked rubber. The long chain molecules now form an entangled mesh which provides resistance to the motion. As a result, a plateau in stiffness is observed. This regime is called the rubbery regime and the relaxation mechanism is very similar to the entropic or rubber-like elasticity. At very long times of deformation, all the molecules have enough free volume and it can relax back to its equilibrium very fast. The long chains slip past each other, essentially flowing like a viscous liquid. This regime is called the terminal flow or the viscous regime. Instead of varying time, this entire viscoelastic behavior can also be observed at constant rate of deformation, just by increasing the temperature of the system. We will talk about the time and temperature similarity later in the video.
A convenient way of developing time-dependent viscoelastic response to visualize the molecular motions is to employ models consisting of spring and dashboard. One way we can model the elastic property of a solid is by using a spring. See how the spring stretches a fixed amount when a weight is added. This is caused by the weight which exerts a downward force on the spring which equals to the mass of the weight multiplied by gravity. We can calculate the spring stiffness using Hooke's law. Hooke's law states that the force on the spring is equal to the stiffness of the spring times the changes in spring length caused by the added weight. There's very little change in the spring stiffness. This is why the elastic spring returns its original position when the weights are removed. Unlike solids, liquids tend to take the shape of their containers. Liquids respond to the forces by continuous moving. Over time, an applied downward force again equals to the mass of the weight multiplied by gravity, will cause the change of the length of the dashboard. This force equals to the viscosity of the fluid in the dashboard multiplied by the rate of change in the dashboard length, which is velocity. When the weights are removed, unlike spring, the dashboard does not return to its original shape. Models were developed by the physics to simulate the viscoelastic behavior of materials. Maxwell, Kelvin-White, and Berger's model are the common ones used to describe the viscoelastic materials. A viscoelastic model was firstly put forward by British scientist Maxwell in 1867. The model shows both the properties of elasticity and viscosity. The model can be represented by a purely viscous dashboard and a purely elastic spring connecting series. The spring reflects the elasticity of materials, which can be mathematically explained by Hooke's law. On the other hand, the dashboard simulates the viscous properties, which are usually given as Newton's law. We can combine dashboard and springs in various manners to make different models. Similar to the Maxwell model, the Kelvin-White model are often used to describe viscoelasticity. Viscoelastic materials usually have very long chains with different molecular weight, so the behavior can become quite complicated, and it's found to have many relaxation times. These materials can be characterized by combination of the fundamental models. Berger's model and the generalized Maxwell model are some of them. The Berger's model consists of Maxwell unit and a Kelvin-White unit connecting series, and the generalized Maxwell model has infinite Maxwell unit connecting parallel. Once obtained the models in hand, the scientists start to think about how to use these models to characterize and predict the viscoelasticity of materials. A stress relaxation and the creep tests are the common methods to characterize the time-dependent behavior. Everybody must be familiar with the stress relaxation when you jump off from a stage. At the moment of touching the ground, you will feel that our feet experience the highest stress. However, you will not feel that big stress after some time because the stress in our muscles and joints relaxes. So the stress relaxation protects us from being injured. A stress relaxation test can be done by providing the material's deformation. The stress response is measured and recorded with time. Before diving any into details, let us review back the Hooke's law. For elastic material, the coefficient E or G is constant. However, for viscoelastic materials, G is changing over time. G is called the modulus, which is an inherent property of a material, which can reflect the stiffness. Modulus is defined as the ratio of stress to strain. In the case of time-varying stress arising from a constant strain, the ratio is the relaxation modulus. Let's take a rubber band. In the stress relaxation test, a constant deformation or strain was applied to the rubber band at the beginning of the experiment. The stress becomes extremely high when the deformation happens, then gradually decreases and changing to an equilibrium value. Compared to the stress time curve, modulus G also changes in the same fashion. At short times, the stress is at high plateau corresponding to a glassy modulus and then falls exponentially to a lower equilibrium rubbery modulus as the polymer molecules gradually accommodate the strain by the conformational extension rather than bond distortion. The relaxation time is also obtained from the stress relaxation plot. Another important testing technique is creep. Compared to the stress relaxation, a constant stress is applied to the material to be tested. The deformation, which is the strain, is measured and recorded. Strain versus time curve can be finally obtained in creeping test. To start a creeping test, a constant stress or load was applied at the beginning of the experiment. Let's watch the strain. The strain increased fast when the load was just applied. Then the strain rate gradually decreases and at the end reaches an equilibrium value. The ratio of strain to stress is called compliance. In the case of time-varying strain arising from constant stress, the ratio is a creep compliance. Upon loading, the material strains initially to the glassy compliance. This is elastic deformation, corresponding to bond distortion. In time, the compliance rises to an equilibrium of rubbery value, corresponding to the rubbery extension of the material. The retardation time is also obtained from the creep curve. Human body is the tallest in the morning and shortest in the evening due to creep under its own weight. When people is sleeping, it recovers. For viscoelastic materials, when the load was removed, the stress starts to recover but doesn't recover completely. The creep curve can be divided into three regions. The primary region is characterized by transient creep with decreasing strain rate due to the creep resistance of the material, increasing due to the material deformation. The secondary region is characterized by steady-state creep where competing mechanism of strain hardening and recovering may be occur. The tertiary region is characterized by increasing creep strain rate in which nicking under constant load or consolidational failure mechanism occur prior to failure of the test piece. Sometimes, quaternary regions are included in the analysis of the strain time curves as well, although these regions are very specific and of very short duration. What will happen if we apply the strain at constant strain rate? A stress strain curve was plotted for the material. From the stress strain curve, we can have a better understanding of viscoelasticity. If the creep strains for various stresses produced at a given time are plotted as a x-axis against the applied stress as a y-axis, an isochronous stress strain curve would be produced. Similar curves can also be obtained from the stress relaxation plots. If the material is linear, this curve will be a straight line, with a slope that increases as the chosen time is decreased. Purely elastic materials do not dissipate energy or heat when a load is applied, then removed. However, a viscoelastic substance loses energy when a load is applied, then removed. Hysteresis is observed in the stress strain curve, with the area inside the loop being equal to the energy lost during the loading and unloading cycle. Stress relaxation and creep tests are convenient for studying material response at long times, but less accurate at shorter times. Behavior similar to what we observed with the syllabody can be found by applying a sinusoidal stress or strain in a dynamic test. In this test, for viscoelastic material, the strain lags the stress by the phase angle delta independent of chosen controlled variable. Upon increasing the frequency, the material chooses to behave more solid-like, which means it can have a high modulus. However, if the strain rate or frequency is low, the material tends to behave like a liquid. As we have talked before, the viscoelastic materials behave as both elastic solids and viscous liquid. So, from the dynamic test, the elastic and viscous aspects can be extracted. The modulus G of a material is contributed by two parts. The elastic part G' is named as a storage modulus, which characterizes the solid-like property of a material. In the opposite, the viscous part G' is named as the loss modulus, which reflects liquid-like properties. In another word, the energy dissipation. From the dynamic test, we know that when the frequency increases, the material behaves more solid-like. In the high-frequency region, the G' becomes very high and the G' is low. However, in the low-frequency region, G' and G' behave in the opposite manner. Let's continue to another important topic in viscoelasticity. In designing a material, the most important thing we need to know about is the yield and failure of the material. Yield happens when the strain continuously increases beyond the critical value. At the yield point, a material ceases to deform elastically in a regardable manner and undergoes permanent, irreversible plastic deformation. To some extent, this makes the material lose the durability and not able to provide enough mechanical strength. In an extreme situation, structural rupture will happen.
So now we have some understanding about characterizing the viscoelastic materials with the help of different experimental methods. But measuring the response with time isn't as easy as it looks. Let's take a look why. The figure shows the response of polyisobutylene with time. For any general viscoelastic material, the complete change in properties with time from an elastic or glassy response to a viscous or fluidic response takes around 15 to 20 decades, depending on the material. A decade here means a factor of 10 hours. In the 1940s, Andrews and Tobolsky showed that there was a simple relationship between temperature and time for the mechanical response of a polymer. They showed that the response at longer times were mimicked the same way at higher temperatures. This similarity can be exploited to get the response at very long times by doing the same experiments in a short time span within the experimental limit but at higher temperatures and shifting them horizontally left or right from a reference temperature. The entire spectrum of response obtained by shifting is called a master curve. The horizontal shift factors give the change in viscosity at different temperatures with respect to a reference temperature. To understand what makes this possible, let's go back to the results from dynamic loading experiments. If the excitation frequency is low, or we do the experiment for longer time, the viscous behavior is predominant, and all polymer chains have the time to respond to the applied load within that time period. corresponding to a lower modulus or stiffness of the material and hence a higher fluidity. Similarly, at constant frequency but a higher temperature, the molecules are more energized, which causes an increase in free volume and chain movement, thus reducing the macroscopic modulus. Viscoelastic behavior with temperature is a crucial factor when it comes to measuring the mechanical response and designing high-performance materials. In the September 11 terrorist attacks, it was later found that the Twin Towers collapsed due to creep at a very high temperature. A more common phenomenon is melting of the roads during summer due to change in viscosity of asphalt. Let's see why different materials behave differently at high temperature.
Other than most of the polymers, metals, asphalt, many other materials also show viscoelasticity under some conditions. For example, some metals behave elastically at room temperature. However, they become more and more viscoelastic at higher temperature. In 2005, the Concorde aircraft finished its last flights from London to New York City. As the fastest civil aircraft in the world, it makes it possible to fly from Europe to New York City in less than 2-3 hours.
There at the end of the runway is Concorde 001. 45 knots, 9. Nose come up to 20 degrees, she's airborne. She flies.
Engineering amazingly found that Concorde can have an elongation of 300 mm during each flight. Most of the aircraft was made by aluminum. The high temperature of the aircraft body makes the aluminum become viscoelastic. Similarly, in space shuttle, many parts may experience high stress during launching and cruising. Ignoring the time-dependent behavior in material, designing and manufacturing can lead to a disaster.
The big areas that all spacecraft designers are interested in is something called end-of-life performance. And that means that basically after so many years, of course, your spacecraft is still working. And time-temperature superposition is a technique that we use to try and establish predictions of how the condition of a material at its end of life. In a space environment where we can be anything from minus 175 degrees C in the extreme, all the way up to, if we took examples from Bepi Colombo, which is 300-500 degrees C for solar orbiter, we obviously know that materials can expand and contract across that range. It's really important because we do not get to go and repair a spacecraft. It's not like your car, if a piece breaks on it, we can take it back to the garage and okay, we have to pay, but it's repaired. Now, of course, when someone's paid hundreds of millions of euros to have that mission in space, it's not very good if we say, well, we didn't do our job very well and we misinterpreted where a material would melt or where a material would begin performing less well. So we have to be confident before we launch the spacecraft. And this is why it's really key to understand these fundamentals.
In all the mechanical models and the experimental methods described before, a response function is determined from an applied excitation. All these tools and techniques described before are valid only when the response is linear to the excitation. The linearity is obeyed when two conditions are met. Firstly, stress is proportional to strain, and secondly, the Boltzmann superposition principle. What it means is the response of a material at any time is to be the sum of the responses to excitations imposed at all previous times. This realm of viscoelasticity is called linear viscoelasticity.